Okay, so thank you very much again for coming and for joining the AI Institute and CMC the day for industry. And we have had so far very good presentations by members of the AI Institutes, by partners, and by keynote speakers. I have attended myself a few of these presentations, and I really enjoyed them, and I learned quite a bit from them. It is my pleasure to chair this second session on AI for social good. We have three excellent speakers with us, Alex Wong, Mark Crowley, and Kirsten Duttenhan. And without any more delays here, I would like to introduce Alex Wong, who's going to talk about human-machine collaborative design strategy to efficient deep learning for real-time video expression analysis. So Alex Wong is a professor here at the University of Waterloo. He's the Canada Research Chair in Artificial Intelligence and Medical Imaging. And he's also the co-director of the Vision and Image Processing Research Group. He has published extensively in journals, conference papers, and he has also authored a number of patents in various fields such as computational imaging, artificial intelligence, computer vision, and multimedia systems. His research involves developing artificial intelligence and medical imaging technologies, and while gathering new insights to improve diagnosis, prediction, and understanding of disease, very, very relevant items these days. So without delays, Alex, I would like you to please connect and make your presentation. Thank you.
Perfect. Thank you for the introduction. So I'm going to share my presentation. Are you able to see my presentation?
Yes, we do, Alex.
Perfect. So it's my pleasure to be here today to talk about some of my work in AI for social good. In particular, I'll be talking about one of our main projects in this area, which is a human-machine collaborative design strategy to efficient deep learning for real-time video emotion analysis. And this is part of our work that is generously supported by Microsoft. So just like a quick introduction about the Vision and Image Processing Research Group. We have around 60 plus research personnel with a big focus on operational artificial intelligence, computer vision, computational sensing, and robotics. And we have a huge, extensive collaborations with different sectors from automotive to transportation to healthcare and agriculture. This allows us to get a much better sense into what are some of the social needs right now. We have a number of spin-offs coming from our research group that leverages a lot of the knowledge and understanding of gaps in society to push forward from healthcare to AI to water safety, so on and so forth. And one of the common messages that we get from industry as well as from society is that AI, especially deep learning, is a game-changing but full of challenges to widespread adoption across industries as well as societies in reality in a scalable and trustworthy manner. And that's kind of the model that we live by when we design deep learning as well as other machine learning AI algorithms and solutions. We try to take a very social as well as a real world context behind it. And so why did we focus on emotion discovery? One of the key reasons why we focus on emotion discovery is because of the possibilities that it might have for helping from AI for social good perspective. This could be from situations like detecting and recognizing and understanding facial expression. It's actually a very crucial skill that we take for granted, but a lot of people aren't able to do that. And one of the key things why we focus on the AI kind of driven approach to emotion discovery is to help understand emotion states and recognize conversational cues, such as leverage, levels of interest, speaking terms, level of understanding, which facilitates for a wide variety of different tasks. With one of our main focus to help individuals with autistic spectrum disorder, ASD, who are faced with an impaired ability to infer emotions based on expressions. And so this often raises complexity of societal interactions and may cause increased loneliness and depression. And so what we feel is is that by exploring AI-empowered emotion discovery, it could potentially help those individuals to better understand and learn through the social interactions, as well as assist them in their daily lives. And so what else can emotion discovery help with? So aside from our key aim, which is to assist individuals with ASD, we've also looked into different tasks that might be very useful from driver state monitoring to see, is the driver happy, sad, are they angry, are they frustrated by the traffic, are they drowsy, are they sleeping, for marketing. So really understanding the demographic, let's say looking at a billboard, looking at a sign to see their, I guess, engagement and interaction for things like depression detection, so we could better understand and isolate and identify flags, situations of potential cause of concern to help us help individuals with that need, as well as very useful for things like security checkpoints, ambient interfaces, so you could interact through your not only just your hands, but also have the system understand the way you are actually feeling and engage with a particular interface and modify itself to enable a smoother, better, and more enjoyable UI UX experience. Also useful for empathetic tutoring and so on and so forth. So we see a lot of uses for emotion discovery in this sense. And so the question here is, what's so hard about emotion discovery? Like, why is this even a problem in the first place? Well, one of the thought experiments is, here's an example of an individual. And if I were to ask you, what expression is he expressing here? Well, it's a little ambiguous. You might think, you know, he's a little worried, he might be a little sad, maybe he's thinking about something, so on and so forth. But in reality, what he's actually expressing, and because this is a controlled experience, he's actually expressing a sense of fear. And so this tells you that even though we take for granted the ability to rapidly determine the emotional state or facial expression of an individual, it can actually be very difficult to teach an AI to do the same thing. And so this became a very interesting challenge for us, and to do it in a real-time fashion was a particular challenge, because there are real-world operational requirements when deploying such systems in real-world practical situations. So for example, there are real-time requirements due to the dynamic nature of facial expressions as they relate to emotions, right? Emotions can change, facial expressions can change over time. So being able to detect and identify quickly becomes very useful. So low latency is very important. Low cost is also very important to facilitate for the widespread use of such systems. For example, be them in, let's say, augmented reality systems, mixed reality systems, tablets, phones, computers, and so on and so forth. They need to be small and embedded for ease of use for the end user, as well as, most of all, it needs to be accurate for correct feedback to the users. Because at the end of the day, we definitely don't want a situation where we're expressing and identifying incorrect emotions and conveying that information. And so how do we actually deal with not only just being able to properly detect emotions from facial expressions, but do it in a real-time manner on a small embedded device? So that's the challenge that we have at hand. And of course, even though it's very challenging, as researchers, we always strive towards improving these solutions for social good. And so there is, in fact, hope. And that comes from the notion of human-machine collaborative design. And the idea behind human-machine collaborative design is, can we actually work with explainable AI to design highly efficient, highly accurate, highly dependable deep neural networks based on human-driven design requirements? So it's not human out of the loop, but it's actually human in the loop, where the AI, instead of acting as a automated way of doing it, it acts as a collaborator to work with the human to build a tailored deep neural network that is specifically for that particular task and environment and situation at hand. And with this kind of explainable AI approach, it learns from the operational targets that we set as human designers, as well as the operational prototypes we provide, and explains to what we call a generator on how to design different solutions with different trade-offs that meet those operational needs. And so this human-machine collaborative design approach allows us to iterate with the AI to rapidly build customized solutions tailored for tasks at hand for a fraction of the time usually necessary to do it with greater performance. And so this human-machine collaborative design approach has two main phases, one of which is a principal network design prototype, where a human looks at their specifications, their requirements, and so on and so forth, and outlines and details them to the machine. And then, given this information, the machine-driven design exploration approach will then go through the different types of explorations and identify what is the best neural network architecture for that particular task and design and operational requirements at hand. And this allows us to really develop unique machine-driven networks tailored around human requirements and tasks at hand, as well as discover insights leveraged in the machine-driven exploration process and surface it for greater transparency and trust in the overall design and deployment of such AI systems. And so we leverage this human-machine collaborative design approach for building real-time emotion discovery. And so with a principal network design prototyping, we leverage kind of like a residual kind of connection types of design principles to build the system. And we leverage machine-driven design exploration approach called generative synthesis to determine the macro and micro architectural designs at an individual module level. And that's the power of doing a machine-driven design exploration approach. It's practically impossible for a human to modify and find the best combinations of individual neurons and synapses in an artificial neural network. But on the other hand, with a machine-driven design exploration, we could leverage the raw power and meticulousness of a machine to craft everything at the finest level. And so in this particular study, this project, what we did was we set the operational constraints such that we want to make sure that we achieve a emotion discovery accuracy of at least 92% on a particular data set, as well as ensure that the network architecture complexity was less than 1 million parameters, because this allows us to do embedded edge deployment based on this real-time network. And so this combines the human experience and ingenuity with the speed and meticulous of a machine. And so here's an overview of what it does. So we take the information we have at hand, our operational requirements, our task at hand, what we wanted to do, as well as the operational requirements in terms of speed, compute, and so on and so forth. We pass through this generative synthesis process, which will then iterate between a generator and an inquisitor to determine what are the best neural networks that satisfy those requirements while still achieving really high performance. And the output, as you can see in the middle, is a very highly tailored deep neural network architecture that can then ingest video streams. And what you see on the right is then be able to predict the emotion state or facial expression being conveyed by an individual. And so here is my one of my former students in the video going through different types of expressions and to mimic emotional states, and we're able to in real time augment and convey it, in this case through an emoji. And so this kind of approach is actually very promising because we were able to build what we call emotion net nanoes that had comparable performance to state-of-the-art networks, in fact higher in certain cases, and yet achieve many folds smaller in terms of size. And so what we can see here, we're talking about orders of magnitude smaller in size, but with a good trade-off between performance, all of which meet our operational requirements. And that's the power of a human-machine design collaborative approach for building neural networks. And so here's an example of a neural network that was essentially made by this AI. What you can see is very high macro architecture and micro architecture heterogeneity in the network, which achieves very high efficiency with a very low number of parameters. So we have these very small, very compact designs because it's able to explore and leverage a very strong heterogeneity or very strong diversity in macro architecture and micro architecture designs. What we also see is that there's a mix of convolutional layers with varying shapes and different number of channels per layer, depending on the needs of the network. And so everything is completely tailored and tuned for the task at hand, which is real-time emotion discovery on edge embedded devices. And not only that, we see a very interesting selective long-range connectivity that is largely sparse, so that we have a very nice balance between model expressiveness, ease of training, while maintaining very low computational complexity. And again, that's what this human-machine collaborative design approach really facilitates for. And not only that, we confirmed that it meets our operational requirements because we tested it in a real-time embedded scenario. So using a low-end ARM 64-bit RISC embedded processor, we are able to achieve real-time performance for both of the networks that we've created, both a moderate power usage as well as low power usage. So not only does it work great in theory, it is really working great in practice. And so by being able to build these very highly efficient neural networks for real-time emotion discovery, we're able to move towards what we call a deployable system, which we have nicknamed Aegis. So here's just a general workflow of the Aegis platform. We're given different variety of different data sets, including ones that we have constructed to improve the diversity as well as the quality and balance of different types of data. We're able to then use this to build expression recognition blocks within this Aegis framework, which allows us to have different neural networks for different operational requirements, depending on the hardware scenario. We're able to then build into the Aegis framework an image capture and pre-processing block so that we're able to get time segments from the continuously captured video stream. We're able to then pass it into these neural networks that we've created. And with the emoji augmentation block, we're able to, in real time, augment the appropriate emoji to convey the proper expression and emotion, be it being deployed multimodally, either on a smartphone, on a mixed reality or virtual reality headset, or even just like monitor or computer screen, for example, during video conferences. And so an overview of the Aegis system can be presented as follows. So real-world frames are captured using any camera device, be it a webcam, be it a video cam, or any other sources. Aegis software then actually processes the data on the device directly in an embedded fashion and passes it through the neural network, which also operates from an on-device perspective. Once the predictions are made, the corresponding emoji is chosen and augmented onto the real-world frame. And this real-world frame is then displayed to the user through the application on each of these different types of devices. And so right now, Aegis is still in an early stage, but with the use of Aegis, individuals with autistic spectrum disease will no longer have to guess emotional states. It's able to help them much better understand and hopefully improve social interactions. Of course, further validation studies are needed to verify the benefits of Aegis, but similar studies in the past have shown promising results. Users may not be unwilling to use it in a social setting at first, but it is suggested that it's first used in home for initial training to help them get adapted to this underlying technology. Privacy concerns do still exist, but by not storing any information, not requiring internet access, and doing everything on device, we try to improve privacy as much as possible. And the first iteration is planned for smartphone with emoji augmentations. And so the other thing that we plan on is incorporating with some of our other initiatives in AI power assistance for visual accessibility as well as cognitive accessibility, where you're able to then also interact with speech devices such as smart speakers and so on and so forth. So you're able to capture the underlying environment and take this information and convey it back to the user. So both of these are strong directions that we continue to explore. And not only that, we are also looking at implications of computer vision driven assistive technologies, such as the one that I described, to to kind of weigh and understand their social benefit, as well as what are some of the negative implications that we might want to look into. For example, potential bias for age, gender, race, ethnicity, privacy concerns in terms of exploitation of personal information, obstructiveness of having cameras, trade-off of autonomy and privacy costs, as well as seclusion in development process. So poor device evaluation, age and condition dependencies, inefficiencies in development, and so on and so forth. And so just some parting thoughts before I wrap up. So privacy concerns still exist with all systems involving cameras and internet connectivity. There are positives, but there's also negatives, and we're really taking those to heart by really focusing on device systems that allow all processing and inference as well as visualizations to be done on device to avoid that kind of transfer. Facial expression recognition is really something that most of us take for granted. We're able to look at an individual and we're able to really understand how they feel. But when this impairment comes in, societal interactions really become, I guess, deteriorated, and loneliness and depression can occur. And so we feel that this work aims to be one of the first steps towards assisting individuals with ASD. And we hope that this also helps future researchers build upon the systems to help better the world. And the last thing I'm going to mention is building operational AI solutions you can trust is actually a very difficult thing. And that's one of the key things that really limit a lot of widespread deployment, unless you have the right tools and strategy. And we feel that human-machine collaborative design approach, especially leveraging general synthesis, can help quite a lot. And of course, last but not least, would like to thank Microsoft for the generous support. And I thank everyone here for listening.
Well, thank you, Alex, for an excellent presentation as usual. Alex, there are a few questions that come to mind here. So when you mention facial expression, what is the difference between facial emotion representation or facial expression? How do you differentiate between both of them?
So that's a very good question. So for me, I view facial expression recognition is really kind of like one of the first phases in really understanding emotion. It's not the end all. There's actually many facets. For example, just the way people talk, how they convey their speech, their facial expressions, as well as their behavior during a conversation is really important to get a full profile of an individual's emotion state. So for example, there are situations where a person might be smiling, but they might actually not be feeling too well. So we treat this as kind of the first step. So to keep things short, facial expression recognition is kind of like the starting point, the first step. And one of the things that we aim as we go is to incorporate additional cues, be it gestures, be it speech, be it other kind of forms of information to allow us to better judge emotion.
Yeah, because I mean, nowadays we are communicating with robots. We are communicating with systems that we wish they interact with us seamlessly for a number of reasons. So this facial expression would be one of the components, one of the modules to determine, for instance, the status of the person, his or her emotion, how the robot will interact. So by only facial expression, so the robot or the interacting machine may not know very well exactly what's going on. So you answered the question very well. So this is only one component.
That's correct.
Others that we may need to fuse together to make the system, I mean, seamlessly interactive. So
that's exactly it.
Very good, very good. Yeah. So there is a question by Marty here. He asked, how do you get the data for this project?
Very good question. So fortunately, there's actually a wide number of different data sets from different institutes from around the world that have went through, ethics, that have actually went through very thorough collection processes, and they have been made available through either request or some of them have just been open source. Okay.
Yeah, that's a good answer. Yeah, one last question, Alex, because I don't have one here, but for this type of embedded type of systems, how do you make sure that this type of dynamic, possibly facial expression that goes from one level to another level to another level, sometimes it goes through a whole spectrum of things. How does it handle this type of things? I mean, to implement it on the edge?
Yeah, that's a very good question. And so there's always a fundamental trade-off, because when you have edge, you also have certain constraints in terms of computational requirements, as well as, more importantly, memory requirements. So you can only store so much information at once. And so what we try to do is we actually cut things into segments, and based on those particular segments, we can then kind of infer emotional states or facial expressions. And then with these different facial expressions over time, which actually requires much less memory to store than the actual video frames, we can then create these sequences of expressions and use it and try to learn what the underlying emotion being conveyed, because time is also a very important part. People's facial expressions will change over time. And so taking this temporal information is one of our next steps to really understanding a more complete profile of the spatial temporal characteristics of some of these expressions.
And it's a good point that you are making, Alex, here, because of the confidentiality components. For instance, some people do not want a system to analyze their facial expression on the cloud. So possibly on the edge, if you have an embedded system on the edge, so the system could do it, and then it submits possibly some information about that facial expression without submitting the face or any other type of environment of that particular person.
And that's exactly it. And with a lot of the main advantage of this kind of dual edge cloud kind of deployment is exactly as you said. With a lot, especially in the area of video analytics and surveillance, it's really not I guess, great in many situations to stream large amounts of raw video to the cloud for privacy concerns. But by extracting metadata, for example, position information, pose information, the privacy of the individuals are still being kept, but important logistic information can then be conveyed for further processing and understanding.
Excellent. Excellent. There is one question from one of the speakers here, from one of the attendees. Could the speaker explain a little more about machine-tailored networks? What do you mean by that? So if that's what he's asking.
Yes, a very good question. So traditionally, most of the neural networks that you see around that are being used are what we call handcrafted neural networks. So that means a designer sat down and thought about what are the fundamental building blocks, how to put them together, what is the overall macro architecture, as well as what is the micro architecture. So everything needs to be handcrafted. But one of the problems with handcrafting everything is that it's very difficult to completely tailor it for your task and system at hand. So what ends up happening is that most people use existing architectures in literature, and they use it as a backbone, and they build upon it to build their custom systems. And at the end of the day, when you do something like that, it's very hard to take into account operational requirements. What if you need something that's extremely efficient? It needs to run on the edge. It needs to be super fast, very low latency. It's hard to take all that into account, and it also is not tailored for a particular task at hand. I might have 5 different tasks that use the same backbone, and so clearly that backbone is not great for every single task. So with the notion of machine-tailored networks, what we do is we provide data as well as operational requirements. We need it to be this small, we need to be this fast, we need to meet certain requirements that be deployed on this particular piece of hardware, and then the underlying machine will take all this information, learn from it, and tailor and create and generate a highly customized network that's really great for the task and data you have at hand. And so that's what I mean by machine tailored, because at the end of the day, it's impossible for me as a designer to craft every neuron and every synapse in a neural network. However, a machine is able to do that with very fast speed.
Very good, yeah. Thank you very much, Alex. I think we should be done with this presentation. We really appreciate your insight.